Okay, so today's presentation is on trace elements, all the stuff besides NP and K, right? Nitrogen, phosphorus, and potassium that plants need. I want to impart on you guys a different way of thinking about soil fertility that's different from what's conventionally taught. Okay, so let's talk about what soil fertility is first, right? I'll just read the prepared text here. Soil fertility, with regards to permaculture, depends on soil services provided by the soil biome. Fertility is essentially means productivity and fecundity, the ability of these plants to be fertile, to produce seed, to reproduce, right? These depend on both macronutrients and micronutrients, not just to the plants, but to the soil biome. Fertility is sustainable if the soil provides the services. It is not sustainable if humans must compensate for a dead or dying biome with constant inputs. So if you think about the way a conventional farm is run, where they keep taking from the soil and the soil is depleted, nothing will grow unless you add fertilizer, but when you add fertilizer, you get this big green crop, and it looks like you're doing okay. And really what you're doing is, on the farm that's operating that way, you're kind of living hand to mouth. As soon as you cut off the input, your farm collapses, right? Well, the problem is, in a typical American farm, the fertilizer utilization efficiency is about 30%. 70% of the fertilizer that's being applied is being lost to leachate, like runoff or off-gassing. And that's a tremendous environmental impact, right? And furthermore, it's just wasteful. Can you imagine paying for fertilizer and expecting 70% of that just to be wasted, right? So we're going to take a look at how we're going to address permaculture. Basically, how do you do agriculture in a manner that's sustainable, that you do in the long run without constant inputs? And interestingly enough, we are talking about input. We're talking about trace mineral inputs, but there's a different way to think about this. So, plant nutrient hierarchy. Let's go take a look at the plant nutrient hierarchy from macro to micro. Air and water provide carbon, oxygen, and hydrogen to your plants. Most of your plants consist of carbohydrates, whether that's fiber that you can't digest, or starches that you can, or sugars, right? Carbohydrates have carbon backbones, so there's oxygen and hydrogen on them. That comes from the air and water. The carbon dioxide from the air is actually what goes into the material of the plant. So back in the day, folks used to think that the material in the plant came from the soil, and it was proven that that's actually not the case. You can take a plant and grow it, like, let's say, hydroponically, and there's no real carbon in the nutrient broth that the plant is growing on, and that plant will still grow and put on mass. Well, where is all that mass coming from? That mass is coming from the air, and also some of the water is being consumed in the production of carbohydrates, but the carbon in the plant is not from the soil. That was proven a long time ago, right? So, the next thing, the macronutrients. This is the stuff that all the fertilizers are about: nitrogen, phosphorus, and potassium. The nitrogen ultimately comes from the air. Our atmosphere is 79% nitrogen, right? The phosphorus and potassium are ultimately mineral, but they're also recycled from dead and decaying organic matter. We'll talk about that later on. And then there are secondary macronutrients. These are like the real bulk macronutrients. The one that is used the most would probably be nitrogen, and in decreasing order, kind of. Calcium, magnesium, and sulfur are not quite micro. They're kind of, I guess, mesonutrients. We can think of it that way. The green in plants is chlorophyll, right? And in the middle of every chlorophyll protein is a magnesium ion. If the soil becomes depleted of magnesium, your plant cannot make chlorophyll. But chlorophyll is a tiny fraction of the amount of stuff that's in the plant compared to, let's say, carbon. So that would be the magnesium would be like a secondary nutrient. You have a question?
Yeah, why are carbon, oxygen, and hydrogen not considered macronutrients?
Because they could be maybe considered
like more macro?
Yeah, they're like meganutrients. Like okay. the vast majority of this, it's in the same way that water is not considered a nutrient for humans. We need water to live, but like we're like 70+% water. right? Like if you took all the water away, we'd just be like a piece of jerky, right? So there's like this is such a large fraction that it's not considered a nutrient. It's needed, but it's not really a nutrient, right? The secondary ones are calcium, magnesium, and sulfur. Magnesium is particularly notable for being the very substance in the middle of chlorophyll that makes chlorophyll able to do its thing. Right? And then there are the, yes?
Tonight, are you going to potentially address like the balancing of like secondary nutrients?
I'm not. That's a much more sophisticated topic. I'm doing more of like, I'm trying to establish the way of thinking about these, because the balancing of the nutrients is a lot more complicated. I don't think I fully understand it yet, so yeah, I'm not going to get into that.
But when he does, we'll bring it back.
Yeah. One thing I'm pretty darn good at is learning something complicated and communicating it in an accessible manner without losing accuracy. So, so the micronutrients, these are the ones which well, these are boron, chlorine, copper, iron, manganese, molybdenum, and zinc, right? These guys are used in the production of all sorts of enzymes and all sorts of substances other than carbohydrates, fragrances, hormones, all the stuff that the plants need. It's just like vitamins. Humans can't just subsist on fat, protein, and carbs. We actually need vitamins, right? And for all the functions that we need micronutrients in the same manner plants need their micronutrients, and these are the micronutrients that plants need. But you cannot simply look at these things in isolation and think of this as stuff that you're just feeding the plant. Because, like I mentioned before, the fertility of the soil comes from the fact that the soil biome is, and when I say biome, I'm not just saying the microbiome, not just bacteria, not just archaea. Fungi are technically not micro, because you can see them with your naked eye. You don't need like a microscope to see them. But worms, mesofauna, tiny little insects, all of those guys work together to provide soil services for the plant. And they all have their own nutrient needs as well, right? And there's this entire spectrum of nutrients that you need to feed the guys that feed the plant. And they're not just feeding the plant. Those of you who came to my last talk will remember the whole talk about what plant roots do in the soil. Plant roots do not just passively take from the soil. They give back a lot into the soil. 70%, roughly 70% of the carbohydrates made by a plant over its lifetime end up in the soil. That's like a super majority of the carbohydrates produced by the plants are sweat into the soil as exudates. And those exudates end up feeding fungi and bacteria. And that provides energy for the life forms in the soil that do these soil services for the plants. So what do I mean by soil services? If you take a plant and you sort of like, pull it out of the ground gently so you have, or just maybe in a potted plant, you take the whole thing out and rinse off the root ball in some water, you'll have a certain amount of root mass that you can see, and that's a tremendous amount of surface area. But most of the plants in the world, something like upwards of 90%, are symbiotic with fungi. And the fungi have these hyphae, these thin fiber-like strands that grow throughout the soil. The amount of surface area that the fungi have is something like 10x more than the surface area of the roots. And the roots already have a tremendous amount of surface area. So you can think about like how much surface area that is. The fungi will obtain water and nutrients for the plant that the plant simply does not have enough surface area to absorb. Furthermore, fungi are actually able to break down rock, and plants cannot, right? A lot of the nutrients that plants need, the micronutrients, these guys, are found in rocks. They're found in rocks, and fungi can actually produce enzymes that will break them down. But if you think about what an enzyme is a protein with a catalytic, usually like a metal ion in the middle. Enzymes are proteins that carry out chemical reactions. And a lot of these enzymes, which are needed to mine rock, involve other minerals that you can't just have it in like a vacuum, just have the thing sort of do it. It's, in order to even do these soil services, the soil biome needs a lot of micronutrients, right? So let's take a look at how these nutrient stocks are lost. So, and we'll get to the fungi thing in a couple more slides. So hold that thought for a second. Let's talk about how soil nutrient stocks are lost. The first method the first sort of cause of the loss these nutrient stocks is depletion, basically violating the law of return. So the law of return is this, it's a permaculture principle. The idea is that you have this cycle, right? If you break a cycle and you keep taking things out of the soil and never returning anything, you're going to deplete the soil. It doesn't come out of nowhere. You don't just sort of violate the conservation of mass and new nutrients just like show up. There has to be this cycle, right? But think about the way that like modern food systems are done. We do industrial agriculture. We produce food for millions, not millions, billions of people, right? And at least in the developed countries, and all the developing countries are moving toward this, which is kind of horrifying if you think about it from a picture perspective. But all the developed countries have sewage systems. And what do? We eat all this food that's drawn out all this nutrient from the soil, right? And then we flush it into the ocean. It's just like one way we're pulling things out of the soil, making our use of it, and we're violating the law of return. There was this German architect, Hundertwasser, who here has not heard of Hundertwasser? He's this German architect, and sort of like a philosopher. And there's this very amusing audio clip. I wish I could find it. I couldn't find it online, but he was talking about how like people pray before they eat, but they should really pray before they shit, because they should pray that their poop goes back to the land, right? Because what happens is if you violate the law of return, you will deplete the soil. Right? So one of the ways that you can sort of restore the law of return is your food scraps. Compost your food scraps and return them to the land. Right? It doesn't completely close the loop. The other giant factor is our fecal matter and our urine. And if you are composting that correctly, so you kill all the pathogens and do it properly, right? Then you can actually close the loop. Can you imagine if we took the fecal matter and the urine of the billions of people on Earth and returned it to the land? There would be no fertilizer industry. There would be no fertilizer industry because that stuff doesn't disappear. The nitrogen, the phosphorus, the potassium, all those things are things we need. And when we make use of them and we're done with it, that stuff doesn't disappear. Our waste is basically plant food. I mean, of course, there are pathogens, you got to do it properly, but like you pee out concentrated fertilizer so good that you can't buy stuff as good as that, right? Let's see if I have a breakdown. Let's take a look at, just as an example, the contents of urine, right? Uric acid, bicarbonate ions, creatine, potassium, sodium, chloride, and urea. Now, you'll remember chloride is one of those mesonutrients, right? Potassium is one of those macronutrients. Urea is nitrogen, right? Our waste material consists of a lot of the macronutrients plants need. Why are we throwing this away and then fracking to produce natural gas to synthesize synthetic nitrogen at an enormous cost to the environment? Cornell University had these guys which use these optic cameras mounted on top of their car, and they drove by this one fertilizer factory in Texas. Are you guys been paying attention to the news about the emissions from these? I'm going to make a brief digression because this is so horrifying that everyone should know about this. Cornell fertilizer emissions. Let's see what comes up. Is this loading? One of these little Google cars, and they mounted some cameras that could detect the optic signature of the emissions of methane. And one single fertilizer plant in Texas was emitting 100 times the amount of methane that the EPA claimed the entire industry was emitting. Let that sink in. One single fertilizer plant was emitting 100 times what the EPA said the entire industry was emitting. Can you imagine what the entire industry is emitting?
Was emitting or was allowed to emit?
Of what the EPA claims they are emitting. The EPA is completely corrupted right now.
Yeah.
Basically, we have vandals in power. Right? They do not give a damn, and I think it is basically fatal stupidity. I'm not going to get started on that, otherwise I'll never finish. But suffice it to say that none of this would be necessary. None of this would be necessary if the vast quantities of urine that we flush away were properly utilized. And you know what happens when all this nitrogen ends up in the water? We end up with algae blooms, and then the algae rots, and you end up with a dead zone. And so, like the sewage processing plants spent all this effort to try to get rid of this stuff, which we're then fracking to get natural gas to produce elsewhere. It's like this is like insanity, right? So, anyways, permaculture, right? The idea is that one of the permaculture principles is the law of return. Right? The other question.
This might be a dumb question, but like, are you suggesting we pee in our yards? Because when I see dogs pee in the lawn,
Yes.
it like kills the grass.
Yes, because it's too concentrated. You
Okay.
pee out concentrated fertilizer. The food you eat. Think about all the food you eat that produces that urine. That little bit of urine you produce can fertilize all those plants and more.
Okay.
Right? So you think about like a salad, right? Okay, so people usually think of, for example, a piece of meat as protein, right? But you know, if you think about even leafy greens, think about like cows, they're made of meat, right? Where do they get their protein? They get from grass. Leafy greens consist of somewhere between 5 to 10% protein, which is not as much as a piece of meat, but if you ate a lot of that, it adds up. That 5 to 10% doesn't just disappear. It's not negligible, right? There are people who are completely vegan who eat nothing but plants, and they get plenty of protein, right? And like the ammonia. Let's talk about nitrogen a little bit, because a lot of people don't have like a understanding of the whole nitrogen cycle. Why do plants need nitrogen? Okay, so we are made of protein, mostly. I mean, just we have minerals in us as well, but proteins are made of amino acids, right? Okay, an amino acid has a carboxylic acid group and an amine group. That amine group, you guys, who here knows enough chemistry to know what an amine group is? Need a little bit of background. An amine, right? Okay, so I'm gonna hop to Wikipedia really quick. I'm just gonna do this because this, I want everyone to be informed. Okay, so an amine group is basically nitrogen connected to some sort of backbone with 2 hydrogens connected to it. So let's take a look at an amino acid. Let's look at, let's say, leucine. Okay, so let's take a look at leucine. Leucine is an amino acid. Is an amino acid an acid? Yes. But is it a base? Also yes. This part is the acidic part, this little double bonded oxygen with a hydroxyl group to it. This is the carboxyl group. This part will shed the hydrogen, and that's what makes it an acid. But this part is a base. This is an amine group. The amine group has, you see why it's sort of kinked, it's sort of folded to one side? It's not flat, right? On this side, there's an invisible little electron cloud. And this electron cloud will pull a hydrogen to it, and then this guy will basically, usually pulls that hydrogen off of water and it leaves the OH group, and that's what makes this a base. So an amino acid is a molecule that has a base and an acid on it. And your proteins are made of amino acids. The acid part sticks to the base part, and your ribosomes and your cells link them together to make these long chains of amino acids, and then they fold them together to make the proteins, right? Where does this come from? This is nitrogen. Well, the atmosphere is 79% nitrogen, right? Why can't the plants just yank nitrogen out of the air? Because the nitrogen in the air is triple bonded to itself. And plants can't cleave that triple bond, right? To give you an idea of how strong the bond is, the more energy is released when you form a bond, the stronger that bond is. You guys remember, do you guys ever remember seeing a thermite demonstration where someone put some aluminum powder on top of rust and you light it up and it forms like molten steel, and it's used to, back in the day they used to weld railroad ties together, the rails together, right? If you've never seen a thermite demonstration, you should check that out. But why is thermite releasing so much energy? Well, thermite you've got this rust, you basically have iron oxide, and the aluminum is so greedy for the oxygen that when it bonds to that oxygen, it forms this really, really strong bond. And when that bond is formed, it releases a tremendous amount of energy. It's like if you had like a bowling ball that fell to the ground, it takes a lot more energy to lift it to a high place, but in the course of falling, it releases its energy. Does that sort of make sense? Right? So all of our high explosives contain nitrogen in them. trinitrotoluene, TNT, right? Octonitrocubane, right? Nitroglycerin, these fertilizer bombs, right? All have nitrogen in them. Why is that? Because when you shock nitrogen and it breaks its bonds with with the things it's connected to, when that nitrogen meets another nitrogen, bam! It forms that triple bond, and it releases so much energy that it releases an explosion. To cleave that triple bond, it takes a very, very tremendous amount of energy or some fancy chemistry to cleave that bond, and plants can't do that. And so we're surrounded by nitrogen, but all of it is useless to plants. Plants need it in this form where they can actually do reactions to it. But you can't get this without cleaving that triple bond of the nitrogen that's in the air. And only certain bacteria can do that using trace minerals, which we're going to take a look at. Right?
Well, isn't it also that, like you said, you would have to go through a process to get rid of kill the bacteria in your waste and stuff? You couldn't just poop in your garden.
You could poop in your garden.
Poop in your garden.
If you don't have parasites and pathogens. The composting talk is another talk, but suffice it to say that the pathogens generally can't withstand hot composting, right? If you can compost hot, the pathogens will be killed off by the heat, but the mesophiles and the thermophiles in the compost that can withstand the heat, they'll survive that, and all the pathogens will be killed off. The other way of getting rid of those pathogens is by relying on the collective sort of community immune response of a rich soil biome, right? All the pathogens are selfish and greedy. They will hurt others to benefit themselves. But in a healthy biome, everything is symbiotic, and a healthy biome will reject bad players. That's a general principle. If you get a body that has bubonic plague and you bury it in soil, the earth has this cleansing effect where you can bury things which are infected, and somehow the earth takes care of it, right? 1 teaspoon of soil will have tens of thousands of species of bacteria and archaea and monera and all these other microbes, and they have these interactions with each other, and they will mount collective defenses against bad players that don't behave well. There's a soil science textbook called The Nature and Properties of Soils, the 15th edition. They have an entire chapter on disease suppressive soils. And to get a disease suppressive soil, it has to have a rich and active biome for reasons which are not easily understood because the interactions are so complex. When you have a massive roiling, frothing sort of activity in the soil, pathogens will be suppressed because the other microbes in the soil collectively mount a defense against them, right? So a pathogen that will attack the plant is attacking the food source of a lot of these soil microbes. They will mount a defense on behalf of the plant to protect the food source. It's in the same way that we depend to a large extent on our gut biome for our immune function. It's been estimated, it's hard to put a number to it, but some people try. Some people say something where between 50 and 60% of our immune function comes from our gut bacteria. That's not even our own immune system. Why is that? Because we are the food source. We put food, we're not like they're eating us, but we are the food provider for the garden in our gut. And if we get sick, what are they going to eat, right? So if there's a pathogen in there, if there are things which don't support your body, your microbiome will mount a defense on your behalf if you have a healthy microbiome. Right? So back to this thing.
Awesome. Can I make a comment on the urine?
Yes.
Whereas on a home scale in our gardens and so forth, in permaculture circles, we like to remind ourselves that you're in charge. The way we partner with urine for our own gardens is potentially powerful. It's also true that one of our permaculture allies used to be a regular member of the guild here, worked for the PUC, and he did an assessment of the residents in San Francisco. We have about 1.5 million people on a given day, people commuting in and that kind of thing. And the collective urine that goes through our sewage treatment facility, he estimated that the nitrogen, potassium, phosphorus content, if you were to somehow be able to capture that and then put it on the commercial fertilizer market, it would be something like $300,000 a day.
That's a lot of money a day.
We are pissing away millions of dollars a year.
Yeah. Yeah.
Literally.
Yeah.
And just if you want to get less cynical about it, in Sweden, the Sands Institute, organization, Stockholm Ecological Institute in a town called Tannum, 12,000 people. They have regularly been collecting urine from residents, applying it to fields, and showing equivalent yields to conventional fertilizer. So that's 12,000 people. It's not 1.5 million people, but just to note that scaling this up. And there's efforts in the States here, at the Richard Institute in Vermont, as a community urine capture system. So this idea of like what action can we take, certainly you're in charge.
Yeah.
If you got a garden, I encourage you to take action in whatever way you see fit.
And you don't even treat it?
I want to address that issue. I want to address the question of like the urine. Firstly, the strength of the urine is too constant. If you pee like on the plant itself, firstly, that's kind of gross. But second, you want to dilute it. You definitely want to dilute it. Alternatively, if you have a hay bale and you when you compost, you want to balance the greens and the browns. It's not greens and browns, it's carbonate, like to get more specific, it's carbonaceous material to nitrogenous material. And if you have sawdust or wood shavings or like, dry carbonaceous materials that you would normally have to add greens to properly compost it, you can substitute your urine for the nitrogenous part of it. In fact, your urine has so much of that stuff, like a little bit of urine counts as like all of those greens. So if you just wanted to, if you threw in some finished compost to inoculate your brown material and threw in a little bit of like urine, that will do it for compost. You can compost stuff with no greens at all, using only your urine for the source or no greens, but just the urine for the nitrogen content. Yes?
Just a couple quick thoughts. One thing about urine harvesting too is unfortunately the average American takes 2 pharmaceuticals a day.
Yeah, that is
antibiotics.
Yeah.
Especially if you're on antibiotics watching.
Yeah.
But
Good point.
you can pee on your compost pile.
Yes.
And that's a great thing. And rather than getting rid of the plants, I would just say add more carbon.
Yeah, yeah.
If I have a compost pile that isn't quite kicking off the temperature in 3 days that I want, I'll pee on it.
Yeah.
I'll tell you to do it, but
They told us.
Yeah.
Words out, right now.
Your secret is.
For the record.
To be sure, like the situation with the drugs, that is a point of concern. I don't know this with certainty, but I'm going to speculate a little bit about these. The drugs are biologically active compounds. They're not plastics. They're not like little indestructible things, right? And I strongly suspect when it goes through the composting process, the compost microbes have ways of breaking down things which are biologically active. The one thing I do have concerns about are antibiotics could breed weird resistances and stuff like that. That is a much bigger issue. I am of the opinion that our dependence on antibiotics is unsustainable and sort of eco-abusive. There are better ways of obtaining health than the ways we're doing it. That's a different discussion.
And just to add, detail to the discussion, living in the city of San Francisco, our Department of the Environment here has funded Dr. Gary Anderson at the Anderson Lab in Berkeley, who, in partnership with Stanford, has developed a method to inexpensively assess the ability for aerobic composting to break down pharmaceutical chemistry. And this city has funded a $100,000 project that's in its 4th year. So early returns, we've had Gary Anderson speak to this permaculture guild. He can come back. The early returns from the results from what they're doing are very impressive. Something like 99% breakdown.
Wow.
So it's
So send it through the compost is like
Anaerobic.
I would be
aerobic.
well, because why aerobic? Because oxidation is. Can you imagine if you took all that stuff and incinerated it, right? Aerobic composting is essentially like a chemical burning, breaking down things by oxidation. And if you have these chemicals that could be broken down by oxidation, a hot aerobic composting system is essentially, I would guess what's going on there is that these things are being broken doon by oxidation, just, with some biological facilitation. I'd be curious to see what biochar in compost does.
I should connect you with Gary.
Yeah, because the accelerating effect of the biochar, that would be really curious to see. Okay, so anyways, back to this.
But also in part, are you also sort of implying the need for the heat in the composting pile relative to the breakdown of antibiotics?
I don't know enough about that to speak authoritatively on that. Actually, I'd like to hear that. What's his name again?
Dr. Gary Anderson.
Dr. Gary Anderson. I think he would be able to speak to that. My suspicion is that the heat is I don't think the heat is absolutely necessary. It's like time versus temperature. If you give it enough time, I think it would break down, right? I mean, like, your drugs expire. They expire because, and a lot of them have this little packet that sucks up oxygen, the little oxygen capture and the humidity capture thing, because these drugs eventually break down. I think if you gave enough time, it would break down. It's just that the heat really helps if you're doing it in a quick cycle. Yes?
I really don't want to sidetrack your conversation
Yeah.
or your talk about it, but some heat is necessary, especially if you're trying to do methane capture.
Yeah.
Bacteria that eat methane live in that sweet range between like 120 and 135. And if you say if you do a coal pile, you're kind of making a methane bomb.
However, if you have biochar abates methane emissions like radically because, well, that's a different discussion. That's a whole biochar thing, which I'm not talking about today.
That's why
I'll talk about it if you guys want me to talk about it, but I want
We'll invite you back.
So let's take a look at this. This is just, okay, I just pulled these off the web. These are not my plants, but if you just do a Google search for urine fertilizer, people are like amazed that they're peeing out concentrated fertilizer that you can't buy stuff that's good. It's like the mineral balance of your urine is perfectly balanced for the food crops you eat. Who'd guess that? Well, obviously, what goes in comes out eventually, right? So here's some spinach and here's corn, and these are both rather nitrogen intensive crops. Now, why are they nitrogen intensive? You know that green that you see in the plants, the healthy green leaf stuff? That's protein. There's the chlorophyll molecule is a protein molecule that has an enzyme in there. Right? Enzymes are proteins. It's like this. If you do not have enough nitrogen, your plants will not produce chlorophyll. That's basically, it's as simple as that. Okay, second thing. So we talked about the law of return, right? The second problem is leaching. Soil, soil is unable, if your soil is unable to hold or exchange soluble nutrients, it will leach out. So if your nutrient is not, if any particular nutrient is not soluble, is not dissolved in water, the plants can't take it up. The plants obtain their nutrients by drawing it up through sap. All that is dissolved in water. If a nutrient is not dissolved in water, is not dissolvable in water, it's not soluble, the plants can't use it, right? So, for example, like limestone. Limestone is full of calcium, but it's like calcium carbonate, right? And calcium carbonate is barely soluble. And if you throw a bunch of calcium carbonate in the ground, the plants, I mean, there may be calcium there, but if it's not dissolved, the plants can't really take it up, right? That's one of the reasons why if you have like eggshell and you want it to be immediately available to the plants, dissolve it in some vinegar, dissolve it in some lemon juice. Then it forms a calcium salt, and all these different salts will dissolve in the water, and that's soluble and the plants can take it up. But if a nutrient, whether it's macro or micro or whatever, is soluble, it dissolves in the water. If it rains, if you have torrential rains, right? That stuff dissolves in the water, and what happens? It runs off. So you have this weird paradox where, like, it needs to be soluble for the plant to access, but if it's soluble, it's at risk of being washed away. So how do you address that? I basically said all this, right? Except for this last little part. Cation exchange capacity and anion exchange capacity. Right? If cation, it's spelled like cation, but it's pronounced cation, just for FYI. Okay, so let's talk about salts really quick. So, when we talk about chemistry, there are molecules, there are things which are bonded, one thing bonded to another, right? If you look at what salt consists of, let's just take table salt as an example. Table salt is sodium chloride, right? The sodium and the chloride are not bonded to each other. They're not sharing electrons. What happens is that the chloride straight up steals an electron from the sodium, and now the sodium is positively charged. It doesn't have enough electrons. And the chloride is negatively charged. It has too many electrons, right? But opposites attract. You've got a negatively charged thing, a positively charged thing, and they sort of like stick together. And so a salt crystal, there's no such thing as a molecule of salt. There's not such a thing as a molecule of salt. Salt is basically a bunch of negatively charged things stuck to a bunch of positively charged things. When you stick it in the water, it dissolves. Why would it dissolve? You know how like a water molecule looks kind of like Mickey Mouse, right? It's kind of bent, right? Why is the water molecule bent? Why is it not straight? It's not straight because the reason they're bent away is on the bent side of the water molecule, there's an electron cloud. There's a pair of electrons. And that side with that electron cloud is slightly negatively charged because you got electrons are negatively charged, right? That negatively charged thing will very readily hold on to something positively charged. So if you drop salt in the water, the water molecules tickle apart that piece of salt, and the little positively charged things will stick to those little electron clouds. Now, the other side, you've got these two hydrogens. Hydrogens are protons, right? They're bent together, and that area is slightly positively charged. So water molecules are very good at dissolving ionic substances like salt, table salt, or any other type of salt. A salt is simply a positively charged ion material, basically a cation material, and an anion material sort of stuck together because of opposite charges. They're not bonded to each other, they're just sort of opposite attracts, they're sort of opposite charges holding them together, right? So, all these soluble nutrients, they dissolve in water, but the thing is you don't want them to rinse away, so you need things in your soil to carry out cation exchange. You want something like Velcro, right, to use an analogy. It will hold on to things, but not too tightly, right? Cation exchange capacity means the cations will hold on loosely and but not be held on so tightly that the plants can't pop them off. And anion exchange means all your negatively charged things will be held on loosely and not pop off. So let's talk about some of these cations and anions. Potassium is a cation, it's a positive ion, right? Nitrate is an anion. Right? Phosphorus is an anion. You need both CEC and AEC in your soil. When you have really good ion exchange, those things dissolve into the water, right? But they come across these sites and then they sort of stick to them. And so the water can run off, but not take the nutrients with them. That is really how you get a soil to retain nutrients and not leach out very quickly. Where is all this stuff found? Organic carbon. If your soil has really low levels of organic carbon, it will leach materials out because it doesn't have the sites there that hold on to those nutrients. And whether you're talking about macronutrients or micronutrients, plants can't access them unless they are soluble. But if they're soluble, they'll leach away. So you need a lot of organic carbon. That's what compost is good for. That's what cover crops are good for. When you plant cover crops, remember, plants sweat sugars into the soil. And those feed microbes, and when the microbes break down, all the decomposition and all the organic material going into the soil ultimately contributes to these two capacities. And this is what enables the soil to hold on to materials rather than leaching them out. Right? Let's take a look at some of these micronutrients. Cation and anion nutrients. Right? We're looking at the micronutrients now. Copper, iron, manganese, and zinc are all cations. They're all positively charged. Boron, chlorine, and molybdenum are anion nutrients. If you don't have good AEC and CEC, these guys will dissolve into the water and leach away. Right? Let's talk about what they bind to. So, if you have an acid group, if you guys remember from high school chemistry, an acid is an acid. The thing that defines something as an acid is that it will give up a hydrogen ion. Right? Hydrogen ion is positively charged, but after giving up that hydrogen ion, it can just as readily hold on to another positive ion, such as all these, or potassium, or calcium, or magnesium, or all these other things, right? So that's what a conjugate base does. Conjugate bases of weak organic acids will carry out cation exchange. And also clay particles. Clay is really good for soil fertility. If you have a sandy soil, sandy soils will not have as high a CEC just natively as a clay soil because clay particles have these little charge groups on them that will hold on to these nutrient ions, right? So I want to talk a little bit more about the weak organic acids. In a compost pile, you've got all this bacterial activity going on. One of the general patterns that you'll notice with bacterial fermentation, basically that's what's going on, there's bacterial fermentation going on inside your compost pile, is that bacteria tend to produce weak organic acids. Let me give you a couple of examples most of you may relate to. Sour pickles, lacto-fermented pickles, produces lactic acid, right? Vinegar, there's that blob-like SCOBY-looking thing, the mother of vinegar that you start blopping in your wine to turn into vinegar. The acetobacter will turn alcohol into acetic acid, right? There's all those weird unpronounceable acids in kombucha, right? Bacteria tend to produce weak organic acids, and that's why soil bacteria, you want to feed them things because they produce the weak organic acids which they don't just float around and dissolve away, they actually will stick to things and react with things. And so you've got these little acid groups sticking out there. They weakly give off their hydrogen. It's important that they are weak organic acids because a strong acid immediately dissociates in water, right? It's not like Velcro, it's just sort of like there's like almost no hold at all. Once it gets wet, it dissociates, right? The fact that it will hold on weakly means that if another nutrient ion comes by and sticks to it, it doesn't immediately dissociate. It has a little bit of stickiness. How do plants get that nutrient ion off? Well, plants produce carbohydrates, right? The plant will metabolize a little bit of its own carbohydrates to produce carbon dioxide. When you dissolve carbon dioxide into the water, it forms carbonic acid. That's one of the reasons why, as the carbon dioxide levels in the atmosphere increase, it dissolves into the ocean and it's acidifying the ocean, right? Ocean acidity is another problem with it. Apart from any of the climate change impacts from carbon dioxide, if you increase carbon dioxide in the atmosphere, you're going to acidify the oceans because it dissolves into the water as carbonic acid. Anyways, in the soil solution, what happens is the plant metabolizes a little bit of the carbohydrates it produces, and it releases carbon dioxide into the soil. And when that touches the water, it becomes carbonic acid. Carbonic acid pops off its hydrogen, and that will swap out for that nutrient ion, and that nutrient ion then goes up to the plant root hair. That is the very mechanism of nutrient exchange in the soil, right? So the negatively charged things, these negatively charged things want to stick to positively charged things. Amine groups will pull off a hydrogen, and then that group becomes positively charged, and so the anions will stick to amino groups. They'll stick to overloaded cation exchange sites, we'll talk about that in a second, and they'll also stick to positively charged sites on some kinds of clay. So there's like kaolinite clay has more anion exchange sites than other types of clay. So depending on your region and what types of clay you have in your soil, certain soils are better at holding onto this than others. Right? So long-term versus short-term thinking, right? The short-term view is this: soil has available nutrients and water. Let's get it to that point. So the short-term solution is let's just add the nutrients. Let's just add fertilizer. If you want the soil to be fertile in the long run, you want the soil to provide the soil services, right? So the problem with the short-term view is, if all you're concerned about is whether or not there are soluble nutrients and water, and all you're doing is adding water and nutrients, that's the agricultural equivalent of living hand to mouth. As soon as you stop the inputs, your fertility collapses, right? The long-term view is this: the soil, instead of having the nutrients, you do want it to have nutrients, otherwise nothing will immediately grow. But the long-term view is this: you want the soil to provide nutrients. The soil can provide nutrients and help the plants obtain water. I think I dropped a word or two in there, right? Long-term solutions: feed the soil microbiome and condition the soil. Because the microbiome, actually I should rather say the biome, including the microbes, provide soil services. The fungi will mine minerals, the bacteria will fix nitrogen. You want to feed the things that are doing the services. Because if you do this is a long-term investment in your soil, then your soil will not need fertilizer. Your soil will simply be fertile, right? So this is the agricultural equivalent of having a savings account and passive income, right? So fixing nutrient loss. The first thing is honor the law of return. Compost your food waste and ultimately even your urine and feces, right? We're all here to talk about permaculture. The first thing we should fix is the law of return needs to be honored. The second thing is improve CEC and AEC. And the way you do that is you use your compost. Interestingly enough, here you are solving two problems with one solution here, right? But it might not be enough to just fix this. This is what you need to do on an ongoing basis. If you actually need to fix lost soil fertility, that's where you need to restore the lost nutrients. And you would use trace mineral sources like rock powder or sea minerals to restore trace mineral stocks. So I want to talk a little bit about rock powder and sea minerals for a second. First, let's talk about rock powder. When I say rock powder, I don't mean any sort of rock. There are certain types of rocks that are good and certain types that are not good, right? As a general class, the type of rocks that you want to use are primary igneous rock. primary igneous rock. Primary means nothing else has happened to the rock itself. An example of a primary rock would be something like granite or basalt. Right, those are the two that I know right off the top of my head, but primary igneous rock. Now, a secondary rock is something where a metamorphic process has happened to it. So like shale and slate and these things, some other processes happen, and sometimes these processes cause certain, not nutrients yet, but certain minerals to migrate out of the rock. You don't want to use things like sandstone or limestone or marble because those are metamorphic rocks. Those are like limestone is made from the shells of ancient plankton that has been compressed into like a rock-like stratum, right? And that stuff is almost entirely calcium. So you're not going to get that big, broad spectrum of all these trace minerals. You're just going to get a heck of a lot of calcium and maybe a few other things, right? So the types of rocks that are not useful are things like limestone, marble, and sandstone and things like that. The types of rock that are useful are basalt, granite, possibly there's a type called gneiss. It starts with G, G-N-E-I-S-S, and there's several other types. Yes?
Can I just add just something to bring a smile?
Yeah.
In New York, we used to say the Bronx is nice, but Manhattan is full of schist.
Yes. As for the classifications, I'm not sure whether or not schist I don't know the classification of schist, but basically, yeah. But suffice it to say that if you look up the type of rock that you have access to, it should be a primary rock and it should be an igneous rock. Secondary rocks, if they haven't had any sort of leaching process, may potentially be useful, right? The other source is, okay, well, let me address one more thing about rock powder. Is it sustainable? Because we're talking about permaculture, right? Isn't rock a mined material? If it doesn't grow, it's mined, right? Well, here's the thing. The impact of rock powder is so disproportionate to the amount that you need to use that, like, you don't have to go and mine the rock. As an example, like Ektar actually introduced me to this one particular company. They are recovering overburdens from places which have been abandoned as mines. When they like for example, when they mine certain areas, they have to remove the overburden, and the overburden in a lot of cases is primary igneous rock because they're going after the ore body, right? And they just have piles and piles of rubble that no one's used. It's not like you don't have to go and mine anything else. You have piles of stuff sitting around from the millions upon millions of tons of stuff that has already been mined. So if you're using that material, you're not mining anything new, and it's already been dug up and is already crushed. You blow it up using like dynamite to access the ore body. Like, a little bit goes a long ways. So in that sense, you're not really mining anything. So is it, okay, so the question is it sustainable? Well, in the long cycle of geology, there's always new igneous rock being made by volcanoes, right? And we're nowhere near using up any of just the overburden from mining. California has something like 90, just California, forget about like let alone the rest of the world. California has something on the order of 90 million tons of this material to use. And a little bit goes a long way, right? Remember, we're providing things that go into the soil that will keep doing their thing in the soil as they are being depleted. If you are honoring the law of return, you're not going to be losing it, right? We're talking about restoring something. So if you honor the law of return, doing this will help restore some of the lost nutrient material, but it's not like you're using large quantities of rock powder. Every month, go stick some more in. It's not fertilizer in that sense. You're throwing in a micronutrient that's helping the soil provide services, right?
And then you put more in.
Yeah. Go ahead, good question.
Do you have to keep putting it in eventually?
If you honor the law of return, theoretically, no. Theoretically, no. Practically speaking, it's really hard to do that.
Yeah.
Right? If you are doing a farm, unless you are going around harvesting poop from like all the people who eat, you can't really be 100% sustainable if you're connected to unsustainable systems. It's really, really darn hard. I'd love to have like a kibbutz or some sort of like commune where we all live in harmony with the earth, but if you truly, truly honor the law of return, you would maybe have to do this once in a while. Unfortunately, in our real world, you probably have to do this once every 5 or so years, 4 or 5 years, depending on your rate. But that's not very, that's doable. Once every couple of years, if you restore the lost minerals, that's not that big a deal, right? Or you could do smaller doses every year. That's another alternative, right? Now let's talk about sea minerals.
I was just going to say, moreover, about the California quarries, and if it's near an urban area,
Yeah.
for example, some of the gardens we've done here, we sourced rock flour, rock dust from an active quarry in St. Clair County, which the rock flour is an air pollutant, so they have to keep it wet. It's a cost to them. So 1 ton we were able to acquire for $7. Because it was just basically a polypropylene bag that could carry a ton of material.
That 1 ton will last you a long time.
That's a long time.
Yeah.
Many, many acres of gardens.
Yeah, I mean,
So-
like you apply this thing at the rate of maybe a couple pounds per acre, if I remember correctly. You're not dousing the place in rock powder. You're putting in like really small amounts because these are trace minerals. A lot of these trace minerals in large quantities actually become pollutants, right? So like zinc, beyond a certain point, is not a trace mineral anymore. Like cobalt, okay, so let's talk about cobalt, for example. Vitamin B12, right, has cobalt in it, has a tiny little cobalt ion in the middle, right? But cobalt can be an absolute pollutant if you have it beyond a tiny, tiny little amount, right? All of these things are like nutrients in the micro range, but you get too much, it becomes a pollutant. Same thing with nitrogen. Nitrogen's a fertilizer thing, but you have too much of it, you end up with nitrogen pollutant.
Just one addendum on looking at rock powders and rock flours. It has to do with secondary rock or metamorphic or mixed quarries. This goes back to the question of the balance of the secondary macronutrients. Lime or having calcium, depending on where you're starting from with your mineral balance in your soil, can be really valuable, and then also on an idealized one-time application. So it's not that secondary rock flour is categorically bad. It's less likely to have the trace mineral mix that you might be searching for in terms of replacing nutrients. But sometimes we found some mixed quarries that would be extraordinarily beneficial from a farming perspective, depending on what you're starting with.
Certainly. So it's really, the way to think about it is you want to use the right tool for the right job. If you need to lime your soil, you need to use, a primary rock might not cut it, right?
Do you try to basically test the soil first and then match with the rock powder, or how do you decide?
There are several ways to do this. If your plants are exhibiting deficiencies in any of those trace minerals, right, there's certain symptoms to look for. For example, if your leaves are curling, sometimes you'll see like plants which have this like wrinkly, distorted look. The leaves are not forming the way they are normally supposed to be shaped. That can indicate, as an example, a zinc deficiency. If you have crops where you've got the leaf with these little like yellow stripes, and your plant's not bred to have that. Some plants are bred to have decorative like yellow stripes. If you have weird coloration on your plant, that can indicate a zinc deficiency, as an example, right? A manganese deficiency can so I don't remember all the like examples, but if you look at some of these catalogs of plant diseases, there are symptoms that will indicate one or another sort of deficiency.
But you need to, or can you just apply the generic?
If you apply the rock powder generically, it shouldn't really harm the plant because the plant can't mine the rock. We're going to talk about the role of fungi later. The great thing about this is think about it like food. I'm going to use a food analogy real quick. If you have food on the plate, right? That's like nutrients which are immediately soluble and they're in the soil solution for the plant to use. But if you don't use it, it can go bad or it can rinse away or whatever, right? People come steal your food or something, right? The nutrients which are locked up in the soil biome to be given up to the plant as needed, think about that as food in the fridge, right? Some preparation is needed before you eat it, but it's still fairly accessible. The stuff that's bound up in minerals that the plant cannot access without the help of fungi, that's like stuff in the freezer or that's stuff inside the pantry locked up in cans. So the stuff that's locked up in the deep freeze or in like cans, that's like your food security for the long run. The thing you're going to use in the near future is the stuff in the fridge, and the stuff that's immediately going to be used is the stuff that's on the plate. So to take it to the analogy for the plant, the stuff that's dissolved in the soil solution, when I say soil solution, what I mean is let's say you took soil and you ran in a centrifuge and got all the liquid out. The stuff that's dissolved in the liquid in the soil itself, that's the soil solution, right? And that's stuff that, if the plants don't use it and it rains, that stuff can rinse away. And if you have too much of it, it can burn the plant roots, right? The stuff that is secondary to that is stuff that will, that's stuff in compost or stuff that's bound up in microorganisms that will maybe yield it up when they die and decompose, right? Or when they cycle nutrients. And then the stuff inside minerals and rocks, that stuff, since the plants can't really access it, adding that material within a reasonable amount is not going to, you're not going to overdose the plant because it's just another mineral in the soil. It's just more minerals, right? Yes.
The only thing I'll add to that is, it's a great question. I don't know that if you, especially a primary source rock or trace minerals, I don't believe in the idea of like over hurting your agricultural system by adding it. You can waste a lot of money.
Yeah.
So like boutique basalts and so forth, there's a huge market to order online, very expensive soil analysis, and then amendments that come in fancy little boxes that you can blow through tons of money by over supplying your soil. So that's just, that would be the problem.
Yeah, a little bit goes a long way. Remember, trace minerals, trace. Emphasis on trace. Right? We're not, you don't want like large amounts of copper, like any amount that would actually show up in remember that whole breakdown of urine? You've got things where it's like 0.1%, it's like fractions of a percent. They're really, really, really subtly there, but they're there because they play an important role, right? So anyways, sea minerals. I want to talk about sea minerals. The overwhelmingly dominant mineral in the sea is salt, sodium chloride, right? And if you just apply seawater to your soil, you could overwhelm your plants. Now, there was an uncontrolled experiment where that happened. The tsunami that happened in Southeast Asia in 2004 that killed over 200,000 people in India and also Southeast Asia, right? In Aceh, the Aceh province of Indonesia, I think the entire island was flooded by seawater. And they were afraid it was going to, shoot, now they've salted the land, everything's wrecked. Subsequently, in the following years, it did rain, you got all that other stuff, but the land was seemingly restored. Their crops were incredibly just verdant, and their fields seemed to have been restored by the tsunami. That was like really unexpected and weird, right? One of the sort of DIY permaculture practices that some people do is they dilute seawater. They dilute it a lot. They dilute it I forget what the ratio is. Who here has heard of the whole thing about diluting seawater? Right? I think it's like 1 to 30. It's really, really dilute. It's not like, it's barely any salt in there, right? And a dilute seawater solution, when you're using it in the ground, the sodium is really, really soluble. That eventually washes out, and a lot of other stuff gets caught on the CEC, right? However, there are companies that, because the sodium ultimately you don't want, you can't end up with salt buildup in your soil. You don't have very good drainage and stuff, right? There are companies that will produce concentrated sea minerals. How do they do that? Right? Firstly, you don't want microplastics. There's seawater has a lot of microplastics in it because we've ruined the earth, right? And microplastics are found to have the ability to massively harm your earthworms, right? This is one of the reasons why I'm a little bit hesitant to use gray water from washing clothes. If you have any synthetics, when you wash your clothes, like the lint trap in the dryer, all those little tiny bits of lint that break off of your synthetic microfiber or your REI, recycled fleece or whatever, right? Those little tiny bits of plastic, they're stuck in that lint, that's only a fraction of it. The rest of it is in the water that comes off when you wash your clothes. If you use that to water your garden, you're putting microplastics into the soil. And for a long time, people didn't really look at what the impact was because they thought it's plastic, it's inert, it's not going to biodegrade. Actually, it turns out it does do something. Microplastics are really bad for your worms. They screw your worms up, right? And I am for the use of gray water, but it is not as simple as we think. You might actually want to run it through some sort of filtration system that capture the microplastics. Because, soap has phosphorus in it. A lot of detergents, come on, wake up. A lot of soaps have phosphorus and have other minerals in them, and that is potentially usable stuff. You just don't want the microplastics.
I was just going to say, best practice is a gray water implementation today is to have a microplastics
Yeah, yeah. So
There's good providers now, so.
good to know that those things exist.
Yeah.
I wasn't sure whether or not, but it's good to know that
There's, and finally, we're at a place where we have been building on the performance of the filters.
Yeah.
They need to be replaced fairly frequently. But
Yeah, and that's, it's a damn shame. I'm,
Yeah.
is this earth even
Or
going
you
to be
can
livable
just
generation?
avoid having synthetic clothing.
Yeah, but that's really hard. It's really hard to, I mean, it's hard to get things which are completely free. It's hard to live a plastic-free life. Yes, Nick?
I have a question about in pragmatic terms. I mean, if you have severely depleted agricultural land that has gotten that way over hundreds, generations, then it might be true that it would take a while to even think about the overuse of rock. I mean, the other thing is you don't want to do it at the same time, or when you're maybe even the concept of dovetailing off the synthetic while you're ramping up with the rock. You don't want to do that, right?
I don't have enough practical experience to speak to that matter. One thing I do know about the use of synthetic fertilizers and a lot of other fertilizers is that they harm the very microbiome that is needed to actually enable you to not use them. Phosphorus fertilizer kills the fungi that mine phosphorus. So I mean, what does it mean to ramp down on that? It's like the very use of it is so. I would say unfortunately, I don't have practical experience to speak to this matter. But if I had a piece of depleted land, what I would do is, if I wanted to do it organically, I would apply a lot of compost and I'd grow a cover crop that's known to be symbiotic with a certain fungi, and I'd make sure that the compost is inoculated by that. Like, as an example, rye is very, very symbiotic with arbuscular mycorrhizal fungi. So sometimes you'll plant a rye cover crop along with an inoculant with AM mycorrhizae, and that gets established, and then they'll plant something like is it chicory or I forget. There's certain plants are more symbiotic with other things, and when you plant those cover crops, that puts carbon in the ground. They might not grow so well initially, but once they get a little bit established, you use like a roller crimper to put that down and let that compost in place, and now your soil is maybe able to handle your real crop. And at that point, I would start producing other things. That's a whole different deal. I'm not a farmer. I'm more like a theorist and like a nerd. Right? So,
And if you're making good compost, especially compost that comes from vegetable scrap, you are putting trace minerals back in.
yeah.
Because it's in the compost itself. So
Yeah.
it depends. Some people make compost just from newer sources. That's a bit more
Single
single
source.
source.
Yeah.
But most of us don't do that because we're not going out to stable. Like most people are, we're taking our vegetable scraps, which is a pretty diverse diet with those low microbes we don't.
Yeah. But I would say though that remember, you have to have. Thanks for coming.
Thank you so much.
Yeah. So the thing about the micronutrients which are in things like compost is, remember I talked about there's like a long-term store, right? And then there's like the mid-range store, and there's the stuff that's immediately soluble. The stuff that's in compost would be maybe that mid-range store. For long-term fertility, you also want to introduce stuff that will take time to eventually become available for the plant. That is where the rock powder comes in, right? Or actually, if you really want to go long-term, do something like chunky rock powder. If it's really powderizing about a lot of fine surface area, it becomes accessible more quickly. That's one of the reasons they powderize it. Speeds up the thing a little bit. So let's talk about the problem of solubility. Well, actually, I think I already talked about this, right? They need to be soluble to be accessible, but if they're soluble, they're prone to leaching, right? Increased nutrient exchange and retention, increased insoluble stocks of nutrients, but foster soil fungi. Soil fungi mine insoluble minerals to buy carbohydrates from plants. The fungi and the bacteria in the soil don't just sit there and get carbohydrates for free. They actually, there's a soil economy going on. Fungi will purchase carbohydrates from plants by providing them minerals that the plants cannot access by themselves. Here's an example. There's this Science Direct. I can send you guys the links by email, maybe, if you guys are interested. However, this is not very accessible. This is a scientific journal, and it's mostly talking about mine soil reclamation. But I'm showing this photo because it's indicative of what's going on. If you zoom in on some of these little microscopic bits of rock that are picked out from the soil, you'll find that there are fungal hyphae like lacing the material. And the fungal hyphae will have these little endpoints where they exude enzymes that eat away the rock. They're actually dissolving away the rock and taking up the minerals, sorting through them, finding out what the plants want, and buying carbohydrates from the plants. That's absolutely fascinating. This, when I learned about this, I was just like blown away. There's a soil economy going on there, right?
It's an analog of that, vaguely at least. We've all seen lichen on rocks.
Yes.
Is
Yeah.
that kind of like a commensalism or parasitic?
With lichen, I believe are symbiosis between algae and fungi. And in that case, it's like the fungi are feeding the algae, and it's really, and the lichen is, it's not so much it's like one organism, it's like two organisms which are like inseparable, but not exactly the same thing. It is similar to lichen. Lichen do that thing, but instead of feeding a plant with roots, they're feeding algae that live on them, right?
And they're breaking down the rock here.
Yes.
Very, very, very slowly.
Yeah, they absolutely are breaking down the rock. And here's another microphotograph. Those little stripes, that's fungal hyphae perforating a chunk of rock. Think about that for a second. This is a Scientific American blog entry. Their blog is really a scientist writing an entry. It's not so much a blog. But anyways, the world's largest mining operation is run by fungi. If you sift mineral particles from conifer forest soil, wash them and examine them under a microscope, you will discover a startling detail: tiny tunnels. Right? Fungi do that mining, so you want to be able to, you want to foster soil fungi. You want to foster fungal activity in your soil, and you do that by providing them with rocks they can mine, but also providing all the other stuff that feeds the plants so they can actually exude the carbohydrates that these fungi need to do their thing. Okay, earlier on I was sort of gesticulating around, right? I want to show you a little bit. So this is acetic acid. This is vinegar, right? In the case of acetic acid, it's attached to a methyl group, but in the case of compost and biochar that's gone through the compost state, this group will be bonded to some large carbon structure. So pretend this doesn't exist right now. We're just looking at this group right here. This is the carboxylic group, right? This is the hydrogen on here. In acids, this hydrogen will pop off. In a weak organic acid, it pops off some of the time. It pops off sort of weakly. It can stick back on. It's like a weak fridge magnet. It stick on and pop off sometimes, right? When this guy is removed, another positive ion can stick here. Now, positive ions are not necessarily just like single positive charge. Calcium, when it becomes ionic, when in its ion state, is calcium 2 plus. This is a 1 plus site. If a 2 plus ion sticks here, this part still has a net positive charge, and if it has a net positive charge, it can hold on to an anion nutrient, such as nitrate, phosphate, so on and so forth. That's why calcium plus carboxylic groups or weak organic acids equals anion exchange capacity. That's something you might be interested in if you are very technical, but it's also kind of interesting to know. Now, this is methylamine, also used in synthesizing methamphetamine, but let's talk about that another time. This is methylamine, right? This part is sort of bent down. There's a hydrogen, or there's an electron cloud up here. This cloud up here will pull a hydrogen right off the water, and now this thing is positively charged. And if it's positively charged, an anion can stick to that. So how does this occur in soil? This is where I throw in my obligatory little blurb about biochar. When you compost with biochar, this past February a paper was published by the soil science group at Cornell. Biochar can react to and hold a stunning amount of nitrogen. Something like 600 times more than the next thing on the list, which is like manure. Right? An absolutely stunning amount of ammonia will react with the char, and when ammonia reacts with the char, pretend instead of having hydrogens, that's a big carbon something or other, right? The ammonia will react with the char and form an amine group, which basically means when you compost biochar, that biochar becomes massively, massively capable of doing anion exchange. And anion exchange, if you remember, anion exchange is necessary for exchanging phosphorus, nitrogen, molybdenum, chloride, and something else that I can't remember.
Boron.
Huh? Boron, yes, boron, that's it. And molybdenum is the other one we're going to take a look at. Let's take a look at, I think, okay, this one. Critical micronutrients, molybdenum and iron. This one's important. I talked about all this access to nitrogen before, right? One of the permaculture practices that I presume most of you guys are familiar with is crop rotation, right? When you do crop rotation, you usually want to rotate in a legume because legumes are symbiotic with nitrogen-fixing bacteria. But if you have sufficient molybdenum in your soil and sulfur and iron, you don't necessarily have to do crop rotation because there are about a dozen species of free-living nitrogen-fixing bacteria, which are not symbiotic with legumes. They live free in the soil, right? The one thing all of these things have in common is that they depend on the nitrogenase enzyme. Remember I told you how nitrogen is super hard to cleave? It's got this triple bond, right? In order to break that triple bond, you use a catalyst, and the nitrogenase enzyme has this site over here, which does some weird magic where basically it's able to actually cleave that triple bond without expending a tremendous amount of energy. This is where all the magic happens. And in this structure, you'll see there's a single molybdenum surrounded by, this is called the MoFi protein, Phi being ferrum or iron, right? And Mo being molybdenum. And there's a bunch of sulfur in there. Without sufficient iron and molybdenum in your soil, the free-living nitrogen-fixing bacteria cannot make nitrogenase. This is a bottleneck in the soil's ability to be self-fertilizing. One of the bacteria that does this is azotobacter. And so you mentioned azomite. Azomite is this product that has an unusually high amount of molybdenum in it, right? And azomite is named after azotobacter, but azotobacter is only one of like a dozen different species that does this. Yes?
Can you go back to the Loki?
Yep.
Just your recommendation. I think you should create a T-shirt with that image with an arrow pointing right to the mode that says, "This is where the magic happens."
Seriously.
Serious.
Yeah. So, what I just told you here actually has profound implications. Imagine if your soil were self-fertilizing, right?
It's like a perpetual time.
Yeah, ConAgra would be really upset. Someone would lose a lot of money if your soil were self-fertilizing with regards to nitrogen, right? Not necessarily, the other things eventually you will have to, like phosphorus and potassium, that doesn't come from nowhere. That actually has to come from something. Whereas nitrogen actually is accessible from the air if you can convert it. And you can, the two things which are bottlenecking the conversion of nitrogen by the free-living nitrogen-fixing bacteria, one of them is access to the mineral needed to power that enzyme. And the second thing is electron transfer. And that's why you guys have to come to my biochar talk, because the biochar solves the conductive biochar. When you make biochar hot enough and it becomes graphitic, it becomes electrically conductive, the microbes can transfer electrons directly through the biochar, and it removes the electron transfer bottleneck, and suddenly the activity of the nitrogen-fixing bacteria is massively increased, and so your soil effectively becomes self-fertilizing with regards to nitrogen.
Austin, you're doing the biochar talk at the All Power Labs.
Yes, at Open, kind of. They want me to keep it short, so.
You should the long version. I'm sorry.
How much does it produce?
How much does what produce?
The nitrogen, these bacteria, is it sufficient to maintain like a farm or a garden?
It depends on your climate, depends on your soil type, depends on your crop, depends on what else is in the soil. It's an equation of like 1,000 variables. Maybe not 1,000, a lot of variables. So the thing is, the figure I've heard that is relevant to the crops that we eat, apart from the use of biochar. Biochar would probably, if I had to hazard a guess, I think that with biochar would be entirely self-fertilizing. That's a bold claim, and I know that's not yet verified. That's, I guess I'm hazarding. But apart from the use of an electron transferring mediator, the estimate I heard is that 15% of the nitrogen that you would find in the wild is provided by nitrogen-fixing bacteria. If you increase the amount of molybdenum and iron available through this, you may be able to bump it to something like a third. So, okay, a third. Well, what about the other 2/3? That's what the law of return is about. You cannot, none of this is about breaking the law of return. I'm telling you ways of being able to like reduce your usage of fertilizer, but if you do not honor the law of return, you can't close the cycle. You cannot just endlessly produce nitrogen without, without honoring the law of return. And so this maybe will reduce some of that burden, but you still need to honor the law of return. The other situation is that if you increase the cation exchange capacity, and if you increase the nutrient exchange capacity, both cation and anion exchange capacity of the soil, it enables you to use less fertilizer because, remember I told you before, a poor soil will have a low fertilizer utilization efficiency because a lot of it is lost either as off-gassing due to the production of nitrous oxide or in leaching. So if you have a very, very good AEC and CEC soil, I would think that additional molybdenum and biochar compost might be able to completely close the gap, but don't quote me on that. That's just sort of a guess. Again, I don't have practical experience on the farm gathering data from the farm. I know some of the theory, but
I mean,
yeah,
just
that's
to add to it though, I mean, one of the certain styles of farming aside in certain intensive scenarios where one thing about permaculture design that can add maybe information to the strategy would be that the idea of rotation or specific rotations just for fertility is in permaculture we have, depending, it's all site specific and outcome specific, but intercropping and polycultures that involve multifunctional nitrogen fixing species as a component of fertility, not solely for fertility, but also potentially yielding either other services for attracting pollinators or even a percentage of the crop for yield itself is kind of built into a polycultural kind of permaculture bias. Noted that there are certain situations that, notwithstanding that we do rotations for certain yields for certain circumstances, but like we can potentially obviate the idea of doing specific rotations for nitrogen.
yeah.
If we have a healthy biome and the right kind of balance.
So
Not to mention mostly increasing water holding capacity as well.
yeah, well, water holding capacity is increases in concert with CEC because the carboxylic group is also very hydrophilic. Okay. On the matter of free-living nitrogen-fixing bacteria, the biochar thing is particularly interesting. In the soils in the Amazon, which they've done like X-ray spectroscopy, and they know there's char in there, there is an unusually high proportion of free-living nitrogen-fixing bacteria, and the nitrate levels are unusually high for someone not fertilizing at all. And so, like, my suspicion is, if it is done properly, it might entirely be self-fertilizing. That is subject to verification, but I hold that out there as something that could potentially be done to like put a dent in this crisis that we're doing with the waste of fertilizer and plants emitting 100 times more methane than that's just not acceptable to me. So, yeah.
What about the ever-present concern now about climate change? We haven't even really talked about that.
Yes.
So what can help balance that without going out of its way?
Okay, so there that could actually probably occupy an entire talk, but there are. Let me see if I have any additional slides.
But everything we're talking about so far, if anything, will help that.
Let me see if I can find some things really quick. Okay, wait a second. Did I repeat some slides here?
I think we did the solubility already.
Oh yeah, we already did that. This is the last slide I have in here, and I'll talk about that in just a second when we close this out. Okay, so the whole nitrogen access without adding nitrogen thing, right, is basically what this shows. This is, I pulled this off the web off of someone who planted using rock powder with no additional nitrogen added to their planting. The one on the left seems to have access to more nitrogen. The one on the left has the one on the right has a little tiny bit of chlorosis. The leaves are a little tiny bit yellow, right? And where is that nitrogen coming from? First, the rock powder doesn't have any nitrogen in it, right? And if this is having more nitrogen access than this, that nitrogen difference is coming from nitrogen that's been fixed in the soil. That it's a considerable, like I know I quoted that figure of 15%, but I think it could go a lot higher than that. 15% is what's been observed in the wild. If you deliberately cultivate your soil so it has a lot of the free-living nitrogen-fixing bacteria species, and sufficient molybdenum and sufficient electron transport from the conductive biochar, I think it can be completely closed loop. So, to address your question, climate, right? I want to talk about the climate thing.
Or so we didn't start talking about it yet.
Yeah.
We did.
Well, a little bit.
We're ramping up towards that.
So, with regards to climate, the factors that are involved is that you want to reduce emissions of other potent greenhouse gases, one of which is nitrous oxide, right? Nitrous oxide largely comes from incomplete denitrification of fertilizer. When you apply fertilizer, remember I told you it's like 30% efficiency, right? The remaining 70% is lost either as off gases, either as ammonia gas or as nitrous oxide. Nitrous oxide is 300 times worse than carbon dioxide as a greenhouse gas. Let me see if I can find this real quick.
And biochar is what we did.
Guys, remember this particular, there's this particular article. Meet N2O, the greenhouse gas 300 times worse than CO2. N2O is the greenhouse gas of greatest concern in agriculture, much more than methane. You know when people talk about like the carbon footprint of eating meat, it's not just the methane that the cows burp out. Now there are regenerative agricultural practices where the cow dung is buried in the ground by dung beetles and all that, and you're increasing soil carbon, but we're not talking about that, okay? Because basically 97% of the meat produced in the United States is produced in feedlots. There's that 3% of the meat that's produced in the US is produced regeneratively. So, you know, thumbs up for the regenerative people, but overall, meat is produced on feedlots. Well, the problem is every pound of meat that you eat requires massive poundages of the animal feed. And that animal feed typically is fertilized the same way all of our other crops are fertilized. And if our soil fertilizer utilization efficiency is 30%, think about how much of that is being wasted, right? The carbon footprint, the greenhouse gas footprint, I should rather say, even though this doesn't actually contain the carbon, the greenhouse gas footprint of eating meat largely comes from the N2O, from the fertilizer that's used to raise the crops that are fed to your meat animals, right? So if you use something that obviates the need for using fertilizer because your soil is producing its own nitrogen, right? You're saving this greenhouse gas footprint, but you're also saving the methane footprint from the, remember I mentioned the synthetic ammonium nitrate is produced using natural gas. The fracking industry is horribly leaky, and plus these plants are belching out methane and they're underreporting it, or just self-reporting it, and the EPA doesn't really care because it's run by a vandal. Right? So that's one way you're reducing greenhouse gases. The other way is this. There's a substance called olivine. Have you guys heard of olivine? There are calcium and magnesium bearing minerals that will lock up carbon dioxide and sequester it as a carbonate mineral. Olivine, if we crushed up olivine into sand and spread it along the beaches of the world, we could capture all of the carbon dioxide we put into the atmosphere since industrial times in a matter of a couple of decades. The problem is we don't really have a couple of decades left. But anyways,
there's an olivine project, I forget what it's called.
Yeah, olivine is one of these things which is a natural mineral process. But the thing is, it happens slowly because olivine is another one of these natural, I believe it's an igneous rock that's exposed and it basically naturally weathers at the surface. But there's only so much surface area. When you crush olivine into a powder and you spread that, that stuff reacts with CO2 in the air. And also, you put it on beaches, the tumbling of the waves keeps grinding it up to expose fresh material. And that stuff will react with carbon dioxide to form carbonate minerals, right? Like limestone is calcium carbonate. There's also magnesium carbonate. All these carbonate minerals lock up carbon dioxide. Now, we put carbon dioxide in the air by burning coal, right, and oil. And so one way of sequestering carbon is the whole biochar route. You're making solid black carbon and you're ensuring it in the ground. It's effectively reverse coal mining. Your plant has captured carbon, you made solid black carbon, you're burying it in the ground. And since charcoal doesn't decompose, if you heat it beyond a certain temperature, it forms structures that enzymes microbial enzymes can't digest. It basically does not revert to carbon dioxide unless you burn it. So you effectively put it away for like thousands of years, right? So that's one way of sequestering carbon. You're sequestering not carbon dioxide, but straight up carbon, right? We need to do that because we dug up carbon and stuck it in there. If all we did was took all that carbon dioxide out of the air, every carbon you're taking out is taking 2 oxygens with it, carbon dioxide, right? So we need to sequester carbon, but there is still a place for sequestering carbon dioxide because, you know, all the cement that we make, it releases a tremendous amount of carbon dioxide because they get carbonate minerals like lime, right? And they heat it, and these bicarbonate minerals, when you heat it, like baking soda is sodium bicarbonate. When you heat baking soda, it burps out carbon dioxide, right? And forms sodium carbonate. Well, when you percolate carbon dioxide through water that has baking soda or has sodium carbonate dissolved in it, it will retake that carbon dioxide. So the same sort of thing is happening when you have rock powder. A significant portion of rock powders that are very rich in calcium and magnesium carry out those carbonate mineral things that will capture and react with carbon dioxide and store it as a carbon mineral, right? And then thirdly, well, let me think about my third point. So I mentioned the N2O. I mentioned the N2O reduction from the fertilizer. I mentioned a lot of the
primary productivity. So you mentioned, but you didn't mention that we can actually sequester carbon.
Oh yeah, I mean there's also the productivity of the plant. If your plant is productive, remember I mentioned 70% of the carbohydrates produced by the plant over its lifetime, not necessarily any individual plant, but over its lifetime, 70% of those carbohydrates end up in the soil and they feed soil fungi. And soil fungi store carbon in the form of glomalin. Glomalin is a glycoprotein that stores the majority of organic carbon in the soil. Let me show you this one thing real quick.
So what about the notion of cascade effects? I guess that's subsumed in what you discussed, right? But the like times 10 order of magnitude.
The whole carbon multiplier effect thing?
Yeah.
Yeah, the carbon multiplier effects, I don't know precisely the impact of rock powder on that. A lot more studies have to be done, but basically the carbon multiplier effect idea is this. If you add 1 unit of black carbon to the soil, black carbon being humus, or basically finished compost, biochar that's gone through the composting process, if you add 1 unit of black carbon, it increases the soil's ability to store green carbon, which is plant root exudates, by 10x per unit of black carbon, right? But green carbon is not the plant, it's the plant root exudates, right? And those 10 units of plant root exudates then feed 10 units of white carbon. White carbon is fungal glomalin, basically fungi, right? And so you put a little bit of carbon, but all these biological processes keep storing more and more carbon in your soil. So there's a fantastic book called Kiss the Ground. Who here has not heard of Kiss the Ground? Okay. This book, Kiss the Ground, let me find this real quick. Images.google.com. Kiss the Ground book.
So you're getting the benefit of all this at the same time, all of these effects, just by using a little biochar and then...
Yeah. So biochar, the synergy is this. The real magic combo is this. Send biochar, high temperature conductive biochar, right? Stuff that's been processed over 600 degrees centigrade, right? Send that through compost with rock dust, or rock powder, stone meal, whatever names people have for that, and apply that to the soil. Because you are removing 2 bottlenecks. The electron transfer bottleneck, which is no small matter. The electron transfer bottleneck is a really big deal. And also the access to those trace minerals, which are needed in all those different enzymes. If you remove those 2 bottlenecks, your plants will grow like crazy. And the embodied carbon, as well as the carbon multiplier effect from the carbon you've put in the ground, as well as the additional carbon that's taken up by the soil fungi, that will draw down additional carbon. So that's the carbon drawdown aspect. So you're reducing emissions and you're drawing down more carbon.
So you're working towards regeneration
Yes.
actually over time, which is the ultimate.
Yeah, so that's in the grand scheme of things, that is regenerating the atmosphere. You're drawing down carbon, and you're also regenerating the soil by increasing the carbon content, and you're also restoring a lot of the minerals which are lost because of poor farming practices and the violation of the law of return. Right?
Just my last question.
Yeah.
Would you think that, maybe it's very hard to tease out or prove, that, for example, the biochar and rock powder of some sort at least could be synergistic per se, in a way that you get even more by their association than you would otherwise.
Okay, what association?
If you put them together,
Mhm.
is,
Are the effects additive or multiplicative? I would
Yeah.
expect them to be multiplicative, but again, I don't have practical farm experience in that, and for me to make a claim without having practical experience would be the overstep. But I would strongly suspect it would be synergistic, because the thing is, the effects we've seen from just the conductivity aspect of the biochar is like insane. Who here has not seen my biochar talk? Oh, okay.
Talk, yeah.
Here, let me pop up a quick photo thing. Wait, I just want to show you a photo. You guys should come to my open house thing.
How about we have you come back for the whole biochar talk again next year?
Great, yes, great.
One other thing I just want to ask folks to keep in mind, large impacts related to climate change are very much the result of deforestation and urbanization globally. We're
Yes.
now at a point of pushing up into the 60% of the globe being populations living in cities. So just don't underestimate that
Yes.
within the context of all these conversations.
Yeah.
For me as a New Yorker coming to California, it was kind of shocking to me how few farms have buffer zones of hedgerows or forests, narrow forest buffers along the outer edges of those farm fields.
Mhm. But
Not to mention urban
urbanization.
forestry.
The way to think about climate change and our impact on it is to not oversimplify. And the point you made is fantastic. There are all these factors involved, right? Urbanization is one of them, but urbanization is not. I'd say urbanization ranks under the conversion of land to agricultural land to produce meat, right? I mean, if you look at how much forest, like in Brazil, part of the reason people are burning down the Amazon is because they want to grow soybean and corn to feed cows to produce beef. If people would, eat, like, they don't have to go vegan, but they could just like maybe eat less meat, not eat like a king like every day. Like back in the day, back in the ancient times, they'd slaughter the fattened calf if there were like some gigantic feast day. We're slaughtering the fattened calf like every day now, like you don't live that way and expect to not end up with like coronary heart disease and wrecked lamb. That's not a wise way to live, right? So anyways, back to this thing. Giltrack Farm. They had their composting operation, and one of the things is, this is not a giant windrow of compost, right? You know, a giant windrow, they were hitting temperatures of maybe 130 degrees when they would compost, but when they would turn the compost, it wouldn't quite recover. The temperatures would never get quite back up there, right? But when they added biochar at a rate of 10% by bulk volume, the compost pile started composting really hot. They hit 155 degrees and stayed that hot for most of a month. Their cycle used to be about 6 weeks, because after a while it would just sort of go cold and it was just sitting there. And now that they've added biochar, they had to extend their composting out to 11 weeks. And the material is just fantastically more mature. But the biochar is not being consumed. The bacteria in compost cannot eat the biochar. So why is it getting that hot? It's getting that hot because of several factors. I want to find this other one. The impact of biochar in the soil. People thought for a while it's probably surface area, because charcoal's got lots of surface area. You know what? Zeolites have a lot of surface area, maybe even more than biochar. If there was zeolites in there, you're not getting the same effect. What's going on when you add biochar to the soil? Electron donation capacity, and also electron transfer, which is separate from the electron donation capacity. The thing that was found out is that the biochar, when it's matured in the soil, has these groups called quinone, benzoquinone, and hydroquinone. And those groups can pop electrons on and off, and those facilitate all sorts of chemical reactions that these microbes carry out that need either to give off and store electrons elsewhere or to use electrons in the process. And when you vastly increase that soil service, everything that involves electrons in the soil, which is, turns out just about everything, vastly speeds up. But when the char is made at temperatures high enough to make it conductive, the transfer of electrons through conductive biochar is vastly faster than the low temp biochar stuff. let me see if I'm going to get a little bit nerdy here, but bear with me here. You see figure E over here? Can we zoom in a little bit?
Can I also just, Austin, maybe suggest, do get nerdy and give us a good teaser
Yeah.
for next year.
Okay.
We're at 9 o'clock, so
Okay.
it's quite all right, but
Yeah.
just give us like, we gotta come back for more.
Okay, so the teaser is basically this. Everything that the microbes do in the soil involves electrons. Some of them produce excess electrons, some of them have a deficit of electrons. But the way these microbes resolve their charge imbalances is they grow out these wires called pili, these little microbial wires that they will reach out and touch other microbes with. These wires are made of protein, and it's really expensive for microbes to do that, right? And they're growing them out blindly, and they have to touch a complementary microbe, and the wires are only so long, they can only grow so many of them, and they're not very conductive. But when you make biochar at high enough temperatures, the biochar becomes electrically conductive, because what happens is you end up with, let me see, do I have the picture? You end up with this thing where the microstructure of the char becomes that of graphite. You get these little graphitic sheets, and because graphite is electrically conductive, something contacting that can simply conduct the electron right through that material. So since electrons are the currency of the soil microbiome, a conductive biochar is sort of like microbial Venmo. It's like instant transfers, right? A macroscopic piece of biochar that you can see with your naked eye can have millions of bacteria in contact with it, right? So instead of these bacteria trying to transfer electrons one at a time, you now have electrons, all the electrons in contact, or all the microbes in contact with a piece of biochar just conduct electrons to that piece of char. And so when you throw that into the compost, you get that crazy effect where the compost gets really hot because the microbial economy has been sped up. You remove the electron transfer bottleneck, and all the activity that they do is just vastly faster. You remove the other bottleneck, which is access to these trace minerals, they expect it to kick up even more than that, right? There's all sorts of other, we could talk for a long time about the way fungi use electrons. It turns out fungi also use them, and everything is predicated on these two bottlenecks: electron transfer and access to trace minerals. And if you remove those two bottlenecks, your soil fertility is going to be much better. Anyways, that concludes my talk.
That's amazing.
Come over to our lab.